Okay, good morning. So let us start today's morning session. The first speaker is Professor Otmar Venjakob from Heidelberg, and the title is Serre Duality on Character Varieties and Explicit Reciprocity Laws. So please start.
Thank you very much for this introduction, and I would like to thank the organizers for this wonderful conference. It's so nice to be back in India and meeting up all of you. So my talk is about joint work with Peter Schneider from Münster. And so reciprocity laws, in the sense of Berge, wish to express coproducts or Iwasawa duality pairings by some other means, by certain calculus of power series, differentials, and so on. So today I would like to explain how this recipe somehow can be derived from Serre duality on certain rigid analytic character varieties and some comparison results in periodic Hodge theory. So the setting is as follows. So this is so we fix a finite extension L above QP, and then K might be another complete intermediate field inside the CP, and we fix an element pi L, uniformizer in the ring of integers OL, and the residual, this is isomorphic to FQ, Q elements. And then we fix a Lubin-Tate formal group attached to pi. So in particular, we have an OL action on it, and this induces a character of the absolute Galois group of LGL into OL units, which are called chi LT. And if I take the quotient here, I get an isomorphism of quotient of the Galois group gamma L with the units in OL. So moreover, omega denotes a period of the Cartier dual of the given Lubin-Tate formal group. And then I denote by dg of k the Fréchet algebra of locally L analytic distributions on G, where G is any L analytic Lie group. Only compact groups show up here in my talk. So this is, as usual, the continuous dual of the locally analytic functions on G. Sorry? Yeah, so K is, we will fix at some point, but we have different choices for it. K later on maybe L, maybe CP or something in between. With values in K, yeah, exactly. Yeah. So let me recall on rigid analytic character varieties. So this is work due to Schneider and Teitelbaum a couple of years ago. And they constructed a character variety X over L, which parameterizes locally L analytic characters phi from the group OL into CP star. So I will give an example in a minute. So X is attached to the group OL. That's an L analytic group, of course. And yeah, we have this kind of characters. But you also can attach such a character variety, it's a rigid analytic object, to other groups. This is additive. OL so far is additive, but now I switch to the multiplicative situation also. I put a times there. So either this or which is isomorphic. So this is the one attached to the units of OL. But via my isomorphism here, I can also interpret it as a character variety of gamma L, this group. And I also have versions of it for the higher 1 units. So either just on, so this is attached to the group OL, gamma L. This is 1 plus PNO. But on the other side, I can also consider the subgroup gamma N, which becomes isomorphic to this group under this character, and call it X index gamma N. So they show that actually X, the additive version, is a form of the open unit ball B. This is the open unit ball. If the period omega is contained in K, so the base change to K gives this isomorphism. And let me explain in the simplest case. L equals QP, pi equals P. This is somehow the cyclotomic situation. Then X is just B. And an element Z corresponds to a character from ZP to star by sending A to 1 plus Z. This is a 1 unit to the A. So that's the way you easily can check that this parameters all those characters. So just a point in the open unit ball gives rise to this, to all of those characters if you vary Z. So you can wonder how they constructed for OL. OL is of course as a QP analytic group isomorphic to ZP to the D for the degree D of L over QP. But of course, then you could also just take D copies of B, but they would correspond to QP analytic characters. So in order to make it L analytic, you do the same thing as in complex analysis, where you apply Riemann-Cauchy differential equation to check holomorphy. So what they do is this relation, which can be written down explicitly, they divide out from the default product of B, and they show that you obtain a rigid analytic variety which parameterizes the L analytic ones. And in that way, you can extend those constructions to those other groups. And what is important now is the following. So first of all, we start with the additive distribution algebra. And Schneider Teitelbaum show in their paper, which is called P-adic Fourier theory, that there's a Fourier isomorphism between the distributions and the functions, holomorphic functions on X, say. So this is a Fourier isomorphism. And then they go on to construct using this isomorphism if K is big enough. So this holds for any K. So this is true always. But then the second one, this is the Lewin-Tate isomorphism, as they call it. This requires that omega is contained in K. And then you can identify this with the holomorphic functions on B. And this is a well understood object. And just certain power series in one variable. And so the idea technically for our approach is that we use rigid analytic character varieties which are defined over L. So we try to define all what we do over the base L. But technically, it's sometimes not easy to work over L because only by using this Lewin-Tate isomorphism, we get explicit elements which we can work with. So often we have to base change to K and work over this form B. And this causes a lot of trouble because if you a field K, if you are not in the trigonometric situation, a field K which contains omega is not spherically complete anymore. This is a concept in periodic functional analysis, which helps you to grant that the usual theorems, Banach and so on work. This breaks down and you have to be more careful about the analysis behind it. Okay, but in the end, we are interested in the multiplicative situation. So we consider as a subset those distributions which are concentrated, supported in the subset of the units in OL. That doesn't, this is just a inclusion of distributions. There's no ring structure on it because you mix up different things. And then it turns out that you have a kind of Mellin transform. And I will write it down and explain it in a second. So all these. So first of all, by the action of the, so by the Lewin-Tate formal group law, OL is acting on everything. So in particular, the prime element pi acts on everything, and that operator, which is induced by the action of the prime element, is called phi. So we have an phi operator on all the objects somehow. And then there is a left inverse of this phi operator, which is called psi. And this can be constructed using traces, but I don't want to go into it. It's a kind of left inverse of the phi operator. So this relation, why this corresponds to the psi equals 0 part, this goes as follows, just to get an idea. You decompose OL into PLOL, the maximal ideal, and disjoint union with the units. And this induces direct sum decomposition of the additive distributions into the image phi of the additive distributions plus the multiplicative part. And since psi is the left inverse of phi, you can write down the phi operator in terms of this decomposition somehow. And then phi equals 0 is just this part. That's d of units in OL, the distributions. And that's the way you get this decomposition here. So in the end, yeah, we have to look for elements where phi equals 0 in order to get a distribution on the left-hand side. That's the idea. Now I have to introduce the Robba ring. So for all the character varieties I mentioned here, you can form a so-called Robba ring. So I won't give the general definition, but just refer to the easiest case of the open unit ball. It's curly a y. So y could be b x x gamma l xn and so on. Only for so if this is an open unit ball B, so the rent is not part of it, of course. Then you can consider half open annuli, say of radius r. And now you consider a power series, a Laurent series in one variable, which converge on some such annuli for a certain r. So if r goes to 1, the subvariety becomes smaller and smaller. So you get more and more functions on it. So these are just, there's an infinite part going to the negative side allowed. So that's a Laurent series in Z. And the condition is that this converges on the half open annulus for some r between 0 and strictly smaller than 1. You can also write this So the direct limit just says that for some r, you get something, and then you have an inverse limit. And you can define functions on a closed interval where now S is another radius, and now we have a closed annulus here, and these are the functions on the closed annulus, and you can go with S to 1, then you get the functions on the half open annulus, and the other direction goes into the other thing. So this gives an impression how technically you can work with the Robba ring. These are Banach algebras, and taking the limit gives a Fréchet algebra, and then taking the direct limit gives you a so-called LF space, limit of Fréchet space. And okay, so this exists for all those character varieties, and now I would like to extend the picture over here to the Robba ring. So the Robba ring naturally of X contains O of X, because the functions in that example which converge on all of B. So and of course, if I have an isomorphism of rigid analytic varieties, I also get an isomorphism here. So what I want to do is, in some sense, so the distributions, they contain the usual group algebra of the group OL with coefficients in K. So somehow the group elements are contained in the distribution as, how do you call them? What's the word? As delta distributions, say. And somehow I would like to get an extension of this ring, which under a sort of Fourier isomorphism is isomorphic to the Robba ring. And well, what I do is I just take the ring and define it as the extension. But the point of view is that, so we have the additive distributions. We have, again, OKX here and OKB here. And I said we have this Robba ring over X. And now I define the Robba ring of the group OL. That's just another name, but I want to stress it because somehow in Iwasawa theory, you consider actions of the Iwasawa algebra, or more general of the distribution algebra, you want a group action. And I want to stress that we can consider this object as an extension of the distribution algebra, which extends this group action somehow if it acts on something. And so, as I said, both these are contained here. So this is natural. And of course, we have extensions of those Robba rings here. Well, again, so this I call the LT isomorphism. Well, this is the identity, but I think about it as a Fourier isomorphism. And this can be extended also to the multiplicative version. So we have, yes, go ahead. You are completely right, thank you. So we have gamma LK, which is isomorphic to the multiplicative version. And here we have the Robba ring, the multiplicative of the multiplicative characterization. And so then I call this the Robba ring of gamma L, which is again just this object. But again, I consider somehow the delta distributions of gamma as sitting inside here. Okay, now having defined the Robba ring, so as I mentioned before, OL is acting on everything. So if you consider the decomposition into the units and the positive powers of pi L, then this is the group gamma L somehow, and this is an operator phi L. And so it's natural in this context to consider phi gamma modules over the Robba rings, the various Robba rings. So actually I will consider, so let me write down. This is the category of analytic phi L gamma L modules M over this Robba ring. That means M is free of finite rank. Sometimes in the literature you consider projective ones, but here I restrict to free ones. Anyway, Berge, Hida, and Schneider have shown that the projective ones are automatically free. Finite rank with semi-linear actions by an operator phi and the group gamma L, which commute among each other. And such that so phi is a semi-linear operator, you can linearize it, and then the linearization is assumed to be bijective. So that's a usual phi gamma module over a Robba ring. I required analytic here. So this is the additional statement that Li gamma L. So one can show that you have a derived action on such a module by gamma L. So the Lie group is also acting. And it's always, this map is always QP-linear. But we assume to be L-linear. So this is an analytic phi gamma module. And you also can explain or define what is an étale phi gamma module by the slope filtration of Ketlaya. Sorry? Why I will, so you're right, I will only use two versions. It's either B or X, those two versions. So when we started this project, I guess I already talked about the beginning in the Iwasawa series 2017 about it. We just worked over B. And we figured out a lot of relations by hard calculations and so on. And Peter always insisted that one has to work over the characterization. And so in the end, we extended everything to X. And I will later show you what is the benefit of it. Okay, So it's why are those phi gamma modules so important? Sure. I form the tensor, so it's semi-linear with respect to phi, the operator of R. So this ring has an operator phi, which I call phi L, and so you have your module M, and your tensor with respect to phi over M, and have a map to M, something like R tensor M. I don't know whether it's what I do is correct now. I always stuck. Maybe it's like R phi M of M. So this is a linearization, and so another way of saying is that the image of phi M of the operator phi M is an endomorphism of M, and its image generates M again over the ring R. That's somehow more or less equivalent. Well, no, you just have from the usual action, gamma L on M goes to M. You get an induced action by Lie gamma L on M to M, and this induces this map. So gamma L is an L analytic group. So yeah, so gamma L is a quotient of the Galler group, which is isomorphic to OL star, and so it has a natural analytic structure. And so the Lie algebra of this is just, well, integrally it's OL or L. So yeah. So the purpose of phi gamma modules is the philosophy of Fontaine, that you can replace Galler representations by phi gamma modules, and so in this setting, it's a result of Berge, and then of Berge, Schneider, Hida, to get the following. We have the continuous representations of GL on some L finite dimensional L vector space, and one can define what is analytic here. So you define it by requiring that you can extend such a representation to CP coefficients and get a semilinear representation, and you require that. So you can do it for all embeddings of L into CP, and require that for the non-trivial embeddings, all the resulting representations are trivial. So trivial means that they are base changed from a trivial representation. And then they show that you have equivalences of categories . So this is a classical situation, the original one of Berge. Then Berge, Schneider, and Hida showed that there's an equivalence of categories between those phi gamma modules and those over X. And so in the end, we get also an equivalence of categories between those categories. And usually you call, so if V is here, we have the object D dagger rig of V here and D Degaric of V index X here. Oh, no, the Galois representations are on L vector spaces. So here everything is with regard to L, there's no K. Maybe I have to hurry a little bit. Okay, so that's the way you want to apply it later on to concrete Galois representations. And I already mentioned that an important step is to consider this Meillen transform, an element which satisfies psi equals 0 gives a distribution here. And so now we have a theorem here. Yeah, you could, but let's not trouble about this right now. So if A is an element in OL, I consider the evaluation at A map. So this sends a character to the evaluation of the character at A. This is an element of the additive character variety. So this parameterizes such characters. So the points are the characters, and just evaluating in a point A gives a map here, right? So the first theorem we prove is the following. So M is assumed to be free. So I write it. Now I work over the additive character variety. And if I switch to K, I can identify this with also the Robba ring over B if I want to. Then we show that the psi equals 0 part of M is again a free module, but now over the Robba ring of the group gamma L, and the basis being this map evaluation at 1 times phi applied to Mi, phi of M. So maybe this looks familiar to Iwasawa series. Sometimes this is just, so there it is just something like this. In the cyclotomic situation, it's just some, yeah, it's that easy, but so what we say is the following. On M, we have an action of gamma L. Since it's an analytic, it's quite of standard, but to extend the action to the distributional algebra. There are also some subtleties if K is not spherically complete, but whatever. This is can be settled. But now the issue now in the Robba ring. So in the classical situation, the Robba ring means that you can invert. If you have a topological generator of Cp gamma, then gamma minus 1 can be inverted. That's just the variable t. If you are on an analogous, 0 is not inside it, you can invert t, the variable, because in the Robba ring, you form it like this, actually. And so that's the important issue somehow. We can extend the gamma action on M to an action of the full group Robba ring on it. So that's there are many elements inverted from the distribution algebra. It's much larger, of course, and so but it's still a free object. And so So this extends the Gallo action. And I like to stress that a PhD student, Rustam Steingart, of mine, has proved this for families varying over some Tate algebra. But okay. So important example, we can take the ring itself. Then we get a map, which I call Meilland transform, from the group Robba ring into the psi equals 0 part of the additive ring, just by having lambda acting on evaluation at one map. And the second important example, we can consider differentials, and I get again a similar map going now into the psi equals 0 part of the differentials, sending lambda to lambda times evaluation at 1 d log of x. So it's a logarithm on this characterization. Sorry? MI are generators, just generators. So the point is that I want to express, if this is a generator over this ring for M, then I can explicitly describe a generator over the group Robba ring in terms of the starting generators. So there has been Serre duality for B has been used by Colmes and other people frequently. But the point is that we get some, so it's not quite straightforward. So of course, Peter is the expert of this part. You have a Serre duality on Stein spaces, but the Robba ring is, of course, not a direct object in showing up in Serre duality. So you have to rephrase this limit somehow, going through the definition and use Serre duality for certain subvarieties and bring everything together. I don't have time to explain this, but in the end, we get a pairing, a residue pairing between the Robba ring of y again, x or b. This goes into, so maybe I just write R here. And then we have a residue map going into K. And this is a non-degenerate continuous pairing. So this is geometrically the natural choice to pair it with omega 1, being the dualizing module somehow. But for our purposes, it's convenient to fix an isomorphism by taking d log of the characterization, and this is an isomorphism. And then we get a self-pairing of the Robba ring. And so this is a self-duality. And this induces isomorphisms between the continuous K-linear maps from the Robba ring into K, and this is topological with the ring itself, or if you plug in the Robba ring divided out by the holomorphic function, then it pairs with the holomorphic functions on Y the same way. Okay. And the point is that Serre duality, as any cohomology theory, is of course functorial. So if you vary the characterities, you can show that there are relative trace maps so that the Serre duality is compatible. And this we will use in a second. So in particular, we have this residue map. So the residue map in the case B, this is simply something like ending this to A minus 1, just in the case X equal to B. And but note that in this pairing, we apply a D log Y here also. Yes? Yeah, exactly. You can make the Serre duality completely explicit. And then the omega 1 of R is also some limit of some other omegas which are attached to some holomorphic things. You have to work a little bit. It's not completely straightforward. So this I define to be the dual into omega 1. So if I take M and it's dual in this way, I can just evaluate, go into omega 1 and use the residue map to go into K. So here, M is an analytic gamma module. So I get this pairing for every M. And the same kind of pairing, which I wrote down here for X and B and so on, you have also available for the group versions, gamma L and so on. So if Y equals this group version, we get a pairing between the Robba ring of R gamma paired with the Robba ring of R gamma going into K. So those, as I said, Serre duality is functorial. So I could also take X gamma N here. And so this corresponded to the higher unit groups, but gamma N 1 plus pi N OL is isomorphic to OL. So I first can go to this pairing somehow. And then I can identify this with the pairing of X. And one can show that you can recover the pairing on the top by the other pairings by some Frobenius reciprocity mechanism. So somehow the pairing for gamma L is connected to the pairing for X. And this connection is rather trivial by construction. So this is just using functoriality. But now the following connection is highly non-trivial And it's perhaps the reason why the explicit reciprocity holds. So we show that you have two ways. As I did before, you have a canonical map into the differentials. So just by taking d log of this characterization and then using the multiplicative residue map going to K. But you also have the additive picture with the additive residue map. And we have the omega 1 of the additive Robba ring. And here we have the psi equals 0 part. And now we use that the Meilland transform for omega 1 induces an isomorphism of this Robba ring with the psi equals 0 part below. Now, for some interesting reason, you have to, it just comes out, you have to multiply by this evaluation at -1 map. And then this commutes. So this is a highly non-trivial relation. So this was completely standard, but here implying the Meilland transform, that is the reason why explicit reciprocity holds. I hope I have some time to explain this, because this implies that Q over Q minus 1, so this pairing of gamma L, so gamma L or the multiplicative one is the same. Now I want to stress the group here again. And now you have the Meilland transforms here, which go into the psi equals 0 parts of those modules respectively. You can multiply them, then you don't land, the image doesn't have to be in the psi equals 0 part here, but it doesn't matter. We have a residue map anyway. And so this commutes. So I can express this pairing via the Meilland transform. So this is for the group algebra, a group Robba ring. I can express it via the additive version. That's the in a highly non-trivial way. And I'm running out of time. I have to introduce the Iwasawa pairing. So if I start with M Czech, psi equals 0, I pair with psi equals 0 here, and I define a pairing Iwasawa upper 0. So this goes into the homomorphisms of R gamma L to K, which are the same as R gamma L. And what do? I have an element M Czech M here, and I consider the form residue. So an element lambda in this ring is sent to the residue of lambda acting on X, evaluated in Y, and taking residues. This is a continuous K-linear map here, and this corresponds to an element here, which I call the image, which is the image of this pairing. And okay, now let V be a representation such that its Kummer dual is analytic, then M check is to define the corresponding phi gamma module under the various equivalences of categories, and M then is just the corresponding module of V twisted by tau minus 1, where tau is the character cyclotomic times PLT to the minus 1. And then we have in the Lie algebra, which is the same as L, with the operator nabla, which corresponds to 1 in L here. And with this having said, I can formulate an abstract version of the reciprocity law. So we have this Iwasawa pairing. I will later explain why it's an Iwasawa pairing somehow. And we can apply the Meillin transform to land into omega 1 phi equals 0 here. And now the crucial thing is that we want to compare this with the following object. So I consider in periodic Hodge theory the crystal decrease of this, and also here decrease of minus 1. And so there's a natural pairing on decrease. So this comes out of the Fontaine's formalism. So this decrease pairs into decrease of the character KLT, tensor R psi equals 0. And so we get a duality below here just by the pairing on decrease. And on the phi equals 0 part, I again use a Meillin transform, and so identify it with R gamma L here, which I can just multiply to get an object here. So this is a trivial extension somehow of, or base change of the decrease pairing. And now Berge has shown that up to inverting perhaps the logarithm, there is a comparison isomorphism between those objects. So these are comparison isomorphism in the theory of periodic Hodge theory due to Berge. And so there you have to invert T. So there is some subtlety, but still, and one can show that this factorizes. So we have the Lie algebra acting here, and this is the Meillin transform tensor B, where LB is just this representation. Okay, so this is the abstract reciprocity law that the Iwasawa pairing, which I constructed here, agrees with a rather trivial pairing below, up to using the comparison isomorphism in periodic Hodge theory. And so that is the abstract version, and you may wonder what has this to do with Iwasawa theory. So the point is, and then I probably can stop. You can add m psi equals 1 here, pair it with m psi equals q over pi L here, going into R gamma L, and this is then the true Iwasawa pairing. And this is linked by applying phi minus 1 here and pi over q phi minus 1 here. And so Fontaine's classical result was that this is H1 Iwasawa of the corresponding thing here. So somehow this upper pairing is a pairing on Iwasawa cohomology, and you compare it with a pairing in periodic Hodge theory. And well, I can't explain. So this follows easily from this version, because on the bottom you use Meilland transform to describe this pairing, and that's going on the bottom line. And on the top line you use, so here you use this pairing of gamma L, and since you can compare both, you can easily show that this commutes. And finally, this is the last remark. If you consider this map, then this is the big exponential map defined by Berge and Foucault, generalizing Bernoulli's exponential map. And here, going down, is a regulator map attached to V times omega, which Peter and I define. And so this abstract reciprocity law immediately says that the big exponential map is adjoint to the regulator map. And that was the purpose of our work. Thank you.
Is there an integral version on all this where you work with lattices rather than the vector spaces?
That's a good question, but we don't have any, and so we try to do it. But so you see, very crucial is the Meilland transform, which we used. And so we could prove it over the Robba ring, but integrally, we don't believe it's true. So the problem is that the bases we wrote down are elements which do not live, well, maybe in the, at least not over the B version. Over the X version, I don't know what kind of integral version you can think of.
I suppose that explicit reciprocity laws tend to begin with the local Hilbert pairing, and these all have a similar flavor to these pairings that are defined over local fields. Do they directly generalize that sort of thing, or is it several steps removed?
Well, if I would have given a colloquium style talk, I would have started with the Hilbert pairing, indeed.
Sure.
But here I thought to more experts, I can do it the other way around. So what is the Hilbert pairing is really a cup product on Galois cohomology of local fields, if you like, if you consider it locally, right? And the Iwasawa cohomology is the inverse limit of those cup products somehow. You could think about it like this. And so from the coproducts in the Hilbert pairing, you come to a pairing of Iwasawa cohomology. Of course, it's a generalization of Hilbert stuff. Hilbert stuff precisely cannot put into this context, but and then of course I had a different focus today. Usually, one has now to stress that this map interpolates certain Roch-Carter exponential maps on Galois cohomology. And so this one does also by this adjointness. So this was proved by Berge, and then we can derive an interpolation property here. And so in that sense, this pairing is indeed related to local Tate duality pairings on the bottom. But I only worked on the top somehow right now.
Thank you.
Any other questions? No more questions from online participants? Maybe no. Okay, then let us thank the speakers again.